Hi, in this session we discuss about Jordan-Holder Theorem. This theorem says that the two composition series of a group are equivalent. Let us see what the statement of Jordan-Holder Theorem is. So it states that any two composition series of a finite group are equivalent. We already have seen the definition of an equivalence of two composition series. That means that if G is a finite group and G is not equal to identity, that means G is non-trivial group, and there are two composition series, namely one is G0 contained in G1 contained in and so on Gn-1 contained in Gn is equal to G, and the other composition series is H0 contained in H1 contained in H2 and so on contained in Hm-1 contained in Hm, which is equal to G. These are the two composition series. Then the Jordan-Holder theorem says that these two composition series are equivalent. That means that the number of terms, that means n is equal to m, and there is a 1-1 correspondence between the set of factor groups of both the composition series. That means there is a 1-1 correspondence between the factor groups of the first composition series, which is G1 mod G0, G2 mod G1 and so on, Gn mod Gn-1, and the second set or the factor group of the set of factor group of the second composition series is H1 mod H0, H2 mod H1 and so on, Hm mod Hm-1. And there is a 1-1 correspondence between these two sets and the corresponding factors are isomorphic. So let us see the proof of this theorem. So we prove by induction on order of G. If G is equal to 1, then the result is trivial, or if G is equal to order of G is equal to 2 also, the result is trivial because G is a simple group and the only composition series is identity which is contained in G. So the result, there is only one composition series, so the result is trivial. So for the simplicity of writing the proof, we use the following notation. The notation is tilde to denote R in 1-1 correspondence. That means that a set is tilde another set. That means A is a set and B is another set. A tilde B means the elements of A and elements of B are in 1-1 correspondence and the corresponding factors are isomorphic. That is how tilde indicates. So we are proving by induction on order of G, and when order of G is equal to 1, the result is trivial, and suppose order of G is greater than 1. Now we have two composition series, namely one is in terms of G's and the other one is in terms of H. And suppose in first case we assume that this second last term of both the series are same. That means Gn-1 and Hm-1 are same. That is our assumption. Therefore, up to this is a composition series of Gm-1 and up to this is a composition series of Hm-1. But Hm-1 and Gn-1 are same. Therefore, you have a two composition series of Gn-1, namely G0 contained in G1 contained in Gn-1 and H0 contained in H1 contained in etc. contained in Hm-1. So we have the same thing denoted here. So you have a two composition series of Gn-1. So because order of Gn-1 is less than order of the group, by induction assumption, the number of terms is same. That means n-1 is equal to m-1, which means that n is equal to m. And G1 mod G0, G2 mod G1, that means the composition factors or the factor groups of the first composition series are in 1-1 correspondence between the composition series factor groups of the second composition series. So in this set, if we add Gn mod Gn minus 1 in both the set, so we added Gn minus 1 mod Gn mod Gn minus 1 and Gn mod Gn minus 1, because Hm and Gn are G and Gn minus 1 is equal to Hm minus 1. So both these factors are same. So we add the same factor into this two list. So still there is a 1-1 correspondence between this set and this set, because there is a 1-1 correspondence between these two sets and the corresponding factors are isomorphic. Therefore, adding the same factor at the end of the list, both the lists, we get both these set are there is a 1-1 correspondence between both these set and the corresponding factors are isomorphic. Therefore, the result is true if Gn minus 1 and Hm minus 1 are same. So we assume that Gn minus 1 is not equal to Hm minus 1. So for the simplicity, we use the following notation where m is equal to Gn minus 1, n is equal to Hm minus 1 and k is equal to m intersection n. That means the m is the second last term of the first composition series of G, and Hm minus 1, that is n, is equal to the second last term of the second composition series of G, and you are taking k is equal to intersection of these two groups, m and n. Now you know that m and n are two subgroup of a finite group, so m and n are finite, so m intersection is also finite. That means k is finite, and we know that any finite group has a composition series. So K also has a composition series. Let this composition series be identity equal to K naught, contained in K1, contained in Kt, which is equal to K. So now you know that M and N are the second last term of two composition series. That means both M and N are normal in G. And both the second last term of the composition series of G, that means M is normal in G and N is normal in G by definition. So therefore Mn is also normal in G and M is contained in Mn is contained in G. Because M is the second last term of the composition series, G mod M is simple by definition. Therefore, G mod M is simple means Mn is either equal to G or Mn is either equal to M. So what will happen if Mn is equal to M? So if Mn is equal to M, then N is normal in Mn and Mn is equal to M. That means N is a normal subgroup of M. And since G mod N is simple, N must be equal to M, which is not possible because we assume that N is not equal to M. Therefore, Mn must be G. Therefore, by second isomorphism theorem, M mod M intersection is isomorphic to Mn mod N. And N mod M intersection is M intersection N is isomorphic to Mn mod M. So, but M intersection N is K, we get, and Mn is equal to G, we get M mod K is isomorphic to G mod N and N mod K is isomorphic to G mod M. So, we know that M is equal to Gn minus 1, so the identity is equal to G naught contained in G1 and so on, which is contained in Gn minus 1 is equal to M, is a composition series of M, and identities begin with K naught is contained in K1, contained in etc., contained in Kt, which is equal to K, and K is contained in M because K is equal to M intersection N. And we have seen that M mod K, which is isomorphic to G mod N, and G mod N is simple, therefore M mod K is also simple. So therefore, this is actually a composition series of M and this is also a composition series of M. But order of M is less than order of G. Therefore, by induction assumption, N minus 1 and T plus 1 terms are here. That means here there are N minus 1 terms and here it is t plus 1 term, therefore n minus 1 is equal to t plus 1, and the set of factor groups of the first composition series, that is G1 mod G0, G2 mod G1, etc., Gn minus 1 mod Gn minus 2, and the set of the factor groups of the second composition series of M, namely K1 mod K0, K2 mod K1, etc., Kt mod Kt minus 1, and last is M mod Kt, that means M mod K. There is a 1-1 correspondence between these two sets, and the corresponding factors are isomorphic. This equation or this equivalence, we call it as equation 1. Similarly, if I start with H0 contained in H1 contained in Hm minus 1, and that is same as N, and begin with identity equal to K0 containing K1 containing Kt, which is equal to K, and which is contained in N because K is equal to M intersection N. And we have seen that N mod K is isomorphic to G mod M, that means N mod K is a symbol because G mod M is symbol. So N mod K is symbol, and this each one is a symbol factor, composition factors are symbol. Therefore, this is a second one is also a composition series of N, and first one is also a composition series of N. Because order of N is less than order of G, by induction assumption, M minus 1 is equal to T plus 1. And the corresponding, the set of factor groups of the first composition series of N and the set of factor group of the second composition series of N are in 1-1 correspondence. And the corresponding factors are isomorphic. That means H1, H0, the set H1 mod H0, H2 mod H1, etc., Hm minus 1 mod Hm minus 2, and the set K1 mod K0, K2 mod K1, etc., N mod K are in 1-1 correspondence, and the corresponding factors are isomorphic. So this equivalence, we call it as equation 2. So therefore, we have n minus 1 is same as t plus 1, and m minus 1 is also t plus 1. Therefore, n minus 1 is equal to m minus 1, which means that n is equal to m. Now you take the first set equivalence, or taking first equation, that means this equation, and in both the side we are adding two factor groups. In this list, in both the side we are going to add two factor groups. Okay, namely, only one factor groups we are adding. One is G mod M to both the list. So G mod M, because Gn minus 1 is same as M, this is G mod M, and G mod M added to in the end of both the list. That equation we call it as 3. Similarly, by taking 2 and append the quotient G mod N to both the list. That means in this list we add G mod N into both the list. That means here G mod N and here also G mod N. But it is G mod Hm minus 1 because N is Hm minus 1, and here we are stating it as a G mod N only. So we got two lists which we called as 3 and 4. And in the right hand side of 3 and 4 up to Kt mod Kt minus 1, up to Kt minus Kt minus 1, this set is same. And we have added M mod K and G mod. There are two terms here, M mod K and G mod M, and here it is N mod K and G mod N. So except the last two terms, the right hand side of both the equations, right hand side set, the set which is on the right hand side which has identical except the last two elements. So but we have seen that M mod K is isomorphic to G mod N and N mod K is isomorphic to G mod M. Therefore, the set M mod K G mod N and G mod N and N mod K. So you consider these two sets, then there is a 1-1 correspondence between these two sets, and the corresponding factors are isomorphic because M mod K is isomorphic to G mod N and G mod M is isomorphic to N mod K. So therefore, the right hand side, therefore by 3 and 4, these two set, we have the right hand side of both the 3 and 4 are identical, the equivalent. That means there is a 1-1 correspondence between the right hand side of this set and this set, and the corresponding factors are isomorphic. Therefore, the left hand side and the left hand side of 3 and 4 are in 1-1 correspondence, and the corresponding factors are isomorphic. So we get G1 mod G0, G2 mod G1, etc. G mod Gn minus 1, and H1 mod H0, etc. G mod Hm minus 1 are in 1-1 correspondence, and the corresponding factors are isomorphic. Therefore, by induction assumption, n is equal to m, and the corresponding factors are isomorphic, or there is a 1-1 correspondence between the factor groups of both the composition series. Therefore, the result is true. So thus we have proved that if you have a finite group and if there are two composition series of that finite group, then both the composition series are equivalent. That means that the number of terms in both the composition series are same, and there is a 1-1 correspondence between the set of factor group of the first composition series and the set of factor group of the second composition series. There is a 1-1 correspondence, and the corresponding factors are isomorphic. So in the next session, we discuss about solvable groups. Thank you.